I'm going to be presenting on wavelet methods and climate time series analysis. So first, thinking about climate data as a signal, um, we consider climate data to be a time-dependent signal just because changes in climate data um, are dependent on time. So we can see that with climate change, temperatures have increased over the last couple hundred years, and that's dependent on time. So we can see the increase in temperatures looking at like a larger plot of climate data. We can see the increase dependent on time. So this brings up issues with using the Fourier transform because sometimes those plots aren't as informative because they don't offer information on when changes are taking place uh, in time. Climate data can be thought of as a sampling of analog signals. They also exhibit periodic behavior. So we can see these four equations on the right are all sinusoidal, and these are all used to model different common climate phenomena. They're given by Lau and Wang. So on this slide, we can see pictures of each of the original plots. And then below the original plot, we have the wavelet transform. And then to the right, we have the Fourier transform of each of these original plots. So I'm going to focus on plot C, just because I think this one's the easiest way to show how the wavelet transform can be more informative than the Fourier transform when looking at climate data. So plot C shows an abrupt change in frequency. On the wavelet transform, we can see that there are two different dominant frequencies, and we can see when the change between the two takes place, whereas the Fourier transform shows us that there are two dominant frequencies, but offers no information about when this change takes place. So this is kind of a motivating example of just why we might use wavelet instead of Fourier transform when looking at climate data because of its time dependency. So Lau and Wang use wavelet transform, and they use the continuous Morlet wavelet as an analyzing wavelet. So that a picture of that is shown right here. And they applied this to real data, to temperature anomaly data from 1860 until around 2000. They end up with this really nice spectrogram. And you can see the evolution of dominant frequencies over time. So the dominant frequencies are given by these little black lines in the spectrogram. And on the right, each of the different little dominant frequencies are plotted and then superimposed on each other to reconstruct the climate data. And we can see that this reconstruction matches the actual data relatively well. So that's kind of an application. So you can first take the wavelet transform of the data to get an idea of what's going on and what the dominant frequency patterns are. And then you can use that to reconstruct and come up with a model of climate data. Yeah, so that was an example of wavelet transform on climate data. Ludeckert et al. Use discrete Fourier transform on climate data because the time steps in the data recorded were equal. So there was a yearly record or an annual recording of average temperature anomalies in Central Europe. And because of the equal time steps, so because these are measured every single year, you can use DFT and it still be informative. So you still can't see when exactly, like looking at the DFT plot on the right here, you can't see when the changes are taking place, but you do see that there are 5 dominant frequencies, and the numbers above show how long these frequency patterns last. So I'm going to focus on this 248 right here that spikes right around 0. This makes a lot of sense because for the majority of time from 1750 to 2000, which is about 250 years, you can see that the data is centered mostly around 0 with a spike here at the end. So that makes sense that we see that on the Fourier transform plot. But what's also nice is that a lot of the other frequencies are kind of muddled, like I can't really make them out. But the Fourier transform still gives us an idea of what kind of frequencies are going on and how long they're lasting, even if they don't tell us when the changes are taking place. So it can still be useful in that way. All of this can be used to create climate models, which I touched on a little bit earlier. These are probabilistic models, and they can give us a probability distribution for future climate events, which can be really useful in predicting climate based on different given scenarios. The accuracy of these models is tested through a process called hindcasting, which is really similar to convolution. So we see coarse content come up in this way as well.